Hello, everyone. I'm going to be recording this sort of new video where I will be going over Module 8, the behavior of fluids. So this is what you're going to find. I went over this at the beginning of the semester. I will have a separate video for the practice problems that you can find here. You have some solutions here, but I think it's better if I show you how to do this in a video. Today, I'm just going to go over the basics of fluids, which includes pressure, density, the Pascal principle, the Archimedes principle, and a little bit of the Bernoulli principle. Okay. As you can see, you can find the slides. Every module has had the same, and I hope that the videos have been very helpful, the video lectures. But as I said, I will go over the problems in a separate video, okay? So let's do the PDF. I think it's always the easiest. Let's start with the idea of a fluid. We're going to be discussing fluids in motion. So we're going to talk about the flow of a fluid, the continuity equation, that's at the end. Normally we call that fluid dynamics. And then, but we're going to start with the static fluids, okay? So we're going to talk about pressure, floating objects, and you may have heard before about the Archimedes principle by the famous anecdote of Eureka, when he was trying to measure the amount of gold in a crown, right? And he was in his bathtub, and he realized that the weight of the displaced water is equal to the buoyancy, right? And the idea of buoyancy is very important because I'm sure everybody here has seen that by a floating balloon, by a floating table or whatever in water, or when you see boats or surf, right? You see them floating in water, and depending on the type of mass, depending on the shape, they float or they might actually go down in water, right? You can do the experiment easily in a swimming pool, right, with different objects. So I'm pretty sure many of you have wondered, right? And we have to start with the idea of pressure, which the simple equation is force divided by area, so newtons per meter squared. But the idea of pressure is applied in a lot of daily life situations, like, for example, when people are walking and you have the high heel shoes and they can sink into soft ground. That has to do with the idea of pressure, right? Same force, less area, so more pressure. Okay, remember, if you have pressure F divided by area, the more force on the same area will give more pressure, right? So you may have heard about the idea of don't exert too much pressure because you can break something. That is because pressure is proportional to force. Okay? Now that's why it doesn't happen with a normal shoe, because the area is bigger, right? And that's the idea, by the way. It's not here in the slides, but I remember reading this in other textbooks of, the common, it happens in the Middle East, where people can lay on a bed of nails because the pressure is distributed among all the nails. If you try to do it on one, you can imagine what will happen. But because they have a bed and they are distributed among a large amount of area, the pressure is less. So then the person can easily, right, lay on top of a bed of nails. It's all the idea of pressure, right? So the man weighs more, so he exerts a larger force on the ground. The women weighs less, but the force she exerts is on a much smaller area. And here it is the equation for pressure. The units for pressure, guys, are very different depending on what you, on when you use it, right? Or even which subject. For example, in chemistry, you use pressure in millimeter mercury, right? Because you use the pressure of solutions or gases, right, in tubes. We use PSI in the US for the pressure of tires, right? And then Pascal is basically the SI unit of pressure, which is which by the way is not very common, right? We actually use in science more the atmosphere, right? One atmosphere is about 100,000 pascals. Okay, so we have these conversions between different units of pressure, and again, it depends on which situation you are actually using it. So remember, if the force is in newtons and the area is in meters squared, your pressure will be in pascal. And the unit is given to this famous scientist or physicist who studied the idea of pressure, which is applied in what we know as the Pascal principle, right? And the basic question was, if you have a mass, and this is a nice experiment that you probably have seen in chemistry, if you have taken chemistry, right? You have like a tube, it can be an isolated tube, right? You have a mobile piston on the top and you place a mass. And then that will either come down or you can exert a force and make it go down. The pressure increases. Why? PV equals to nRT. If the volume decreases and you keep everything else constant, the pressure will increase. That's ideal gas law, right? Now, in here we want to know what happens with the pressure exerted on it. Does the pressure have a direction, or does it transfer, right? And that's the idea with the Pascal principle. We can use two pistons. And what we know from the Pascal principle is that the pressure exerted on one is transferred to the other. And it has to do with the conservation of mass and energy, right? Remember, from Newton's second law, force is the rate of change of momentum. But we also know that force and distance is work. And what's work? Energy. So it makes sense that this has to be conserved. Does it transmit a force to the walls or the bottom of the container? So let's take a look, right? Any change in the pressure of the fluid is transmitted uniformly in all directions. So every direction will feel a force, which is why, for example, when you are underwater, the pressure affects in every direction. If you have done scuba diving, or even when you go on an airplane, right, you can feel that pressure difference, right? When you go closer or farther from the ground, above on the sky, the pressure decreases. When you go inside, like underneath, scuba diving, or you go underneath water, right? Or you immerse yourself in a pool or in the ocean, you start feeling pressure in your ears, right? Why is that? That's because besides the equation that you saw of pressure, force divided by area, we can demonstrate that pressure is also a function of the density, gravity, and the height respect to the ground. The closer we are towards the center of the earth, the greater the pressure, which, by the way, explains why we haven't been able to investigate properly the bottom of the oceans, because it's very hard to reach those places. However, if you want to launch a spaceship towards the moon or Mars, it's vacuum. So there is no pressure, no friction, right? I mean, it's still tricky, right? It's still difficult, but it's we don't have to deal with external factors as pressure and temperature, which, as you know, we haven't been able to reach more than beyond the crust, right? The crust of the Earth is about 50 kilometers thick. We have reached, or we have drilled holes, or a hole of about 11 kilometers, as far as I remember, all right, which is a tenth, right? Or which is a fifth of the thickness of the crust. And you know, the crust is a very thin layer compared to the mantle, right? The mantle is about 2,000 kilometers, right? And then, of course, we have the nucleus of the Earth, which is about, well, depending, you have the inner, the outer core, right? But still, so that shows you how difficult, and because of that, because of how pressure acts on not just our bodies, but on any body that is being immersed in large amounts of pressure. So then we can apply this idea in hydraulics. And this is the experiment I was telling you guys about. You have the pistons, one here, one here. You have different areas, and you have different forces. But when you do the ratio of F1 divided by A1 and F2 divided by A2, we realize that it's the same. Why? Because the pressure is transferring every direction uniformly. That's the Pascal principle. All right. Which is basically what you guys use in brakes, or what we use in brakes in real life for a bicycle, right? Or for a car, right? You press the brake, so you're exerting a force, but that force is not enough to stop a car. So how are you stopping the car? Because there is a hydraulic system inside the car that is transferring the pressure that you're exerting towards the braking system, and that exerts a larger force, right? The force F2 here is much larger than F1. So you may not have to apply enough force here, but there is a very tiny area, right? Think about the pedal. So you press it, not too hard, of course, and you have a large amount of pressure. That pressure goes toward the braking system. And because the braking system has a larger area, right, then the force has to be bigger, right? By this equation, if the force is bigger, the area is proportionality. So then that's enough to stop a car. All right, that's basically what this is. Here is some math, right? It says a force of 10 Newton is applied to a piston of this area, the output piston of the... So this one, guys, maybe I can just show you here very quickly. Like, I will do problems of this, of course, but sometimes you don't have to change the units. The way I think about it is 10 divided by 2 equals to F divided by 100. Why not change the unit? Because the units cancel. Centimeter squared cancel with centimeter squared. So then you have 500, right? 500 newtons is equal to F. Right? So, okay, so then when the pressure of the fluid, so that's even easier, we don't even calculate the force. So the pressure is just 10 divided by 2, but, P is equal to force divided by area, but area now has to be, right? So centimeter square, guys, by the way, is 2 divided by 10,000. Okay, because you're doing it centimeter square, 100 is 100, right? So then clearly you're gonna get here 550, 1, 2, 3, 4, 50,000 Pascal, which can be 50 kilo Pascal. And that's the answer there. All right, it's here, right? And here's the conversion, by the way, of area. All right, so if they were asking you for the other force, I just show you here, right? Like the other force, F2. Oh, yeah, so here it is. All right, yeah, so atmospheric pressure. Remember, guys, that as I said, we are always surrounded by air, right? So there is pressure, atmospheric pressure, about 1 atmosphere, all right? And that's at the sea level. If you go at higher altitudes, this air is thinner, right? It's also thinner depending on the weather conditions. That is because there is less pressure as you go up, right? So at the sea level is about 100 kilopascals. So as I said, basically 1 atmosphere. All right, 1 atmosphere is 10,000 pascals. All right, or wait, 100,000 pascals, my bad, right? Because it's 10 to the 5. It's 10 to the 5. I always remember that conversion because we use it a lot in physics and chemistry. So pascals to atmospheres. All right. So this still there is a unit. Oh yeah, 14.7 pounds per square inch. That's PSI. Okay. Remember that, for example, for tires, the recommended pressure is about what? 34, 35 PSIs. So you can already think, how much pressure you need. This is something that you kind of see in chemistry, that Torricelli and the barometer, which is a device that we use to measure pressure. Here it is, millimeter per mercury, right? So this is where the units, the other units for that they use in chemistry come from. All right. So this is a device to measure atmospheric pressure. We have some of these devices in the lab. Normally in chemistry, when you're doing experiments, you need that value, right? So basically, you use mercury. It has a density of 13.6 grams per centimeter cube, and yeah, so it's much more dense, right? The density of water is 1 gram per centimeter cube. So it's much more. So for example, if you have mercury, if you ever work with mercury, any object can easily float because of the high density. So here it is. Density is the mass divided by volume, right? And we talk about density a lot when we talk about fluids, gases, and solids, right? Because it's a parameter that we need to study materials, right? In astronomy, we talk about density to describe singularities, right? A singularity in astronomy is basically a black hole. Why? Because it's a point of infinite density. You have a large amount of mass in basically zero volume, zero, but close to zero, right? So it gives you infinite density, right? Which is the reason why space-time is bent so much that light cannot even escape from it. Um, Air pressure acting on the mercury in the dish support. Yeah, so this is basically the experiment. Here, basically, you just look at the height of the column, how much it moves, and then that's how basically they determine. I believe the conversion is 760 millimeter per mercury to be exactly 1 atmosphere. All right. Okay, so we can. So yeah, so basically, thanks um to the barometer, we can determine that there is evidence of a decrease in the external atmospheric pressure as you go to higher altitudes. All right. Um, Pascal also observed this, right? And also in the stormy days, he realized that there was this relationship, right? Um, well, basically, it's not here, but as I mentioned, the equation for pressure or pressure can also be found by the density of the fluid. Air is a fluid, by the way. The value of gravity times the value of gravity times the height difference. So you normally need like a perspective, right? The barometer, maybe you can place it here and here, and you have two readings. You compare the readings, and then that will give you the height, right? Because the air is the same. The density doesn't change. Gravity is the same. So what changes is the value of height and pressure. So when we talk about air and the weight of air, um, maybe the best way to show you this, besides what they describe here with the density and the mercury as a liquid and air being a compressible fluid and a gas, we can talk about the balloons, right? When we talk about balloons that are filling with helium, right? You will notice that those balloons float and they go towards the sky, right? And the reason is because like air and other gases, right? They have a mass and therefore they have weight. And this is important when we start talking about the Archimedes principle, all right? Because we can discuss and bring into account the idea of buoyancy in air. Okay, now in here it's important to highlight that air has pressure, volume, and density, and they can change because it depend on the temperature. Basically, like an ideal gas. All right, it is a gas, so we can use some of the same relationships, and one of them is basically Boyle's law, right? That the pressure times the volume is a constant if the temperature is constant. All right. Variations in the volume and density of a gas that accompany changes in pressure were studied. Yeah. So the idea was that at constant temperature, pressure and volume were inversely proportional. More pressure means less volume. All right. So that actually makes sense, right? If you think about it, if you have the constant values of temperature and you are decreasing the amount of volume in a given area, right, in a given region, then the pressure will increase, right? That is basically, oh, here it is, right? So the density of a column of air decreases as the altitude increases. Yeah, because of this. All right. So how do we use this? They have to give you situations like situation A and B. Like you have a fixed quantity of gas, that means the same the number of moles don't change. The pressure of the gas is initially 1 atmosphere, so about 100,000 kilopascals, and the volume is 0.3 meter cube. What is the final volume of the gas? The pressure. Okay, that's simple, right? Like there's nothing weird about this problem, right? Let's just erase this for now. Let's bring this down. And PV. So P times V equals to P times V2. So V2 equals to 0.1. Caramba. 0.1 meter cube. Yeah, simple. All right, so I mean, maybe you have seen this in chemistry, Boyle's law. There is also the Charles law when you have pressure over temperature at constant volumes, right? We talk a little bit about that in thermodynamics. There are different situations, constant pressure, constant volume, constant temperature. And then you have like different processes, isobaric, isothermic, adiabatic. That's all when the study of gases, right? Right now we're talking about fluids. And yes, air can be considered as a gas, but it also is considered a fluid, right? Which that's why we can introduce the Archimedes principle, right? The Archimedes principle is basically what I discussed with objects floating in water. Why do they float? Think about Newton's laws. We have to think what forces are acting in the object. And the only two forces are the weight and what else? What's making the object float? Buoyancy. But we didn't know what buoyancy was. We knew that there was a force. It was Archimedes who discovered that a buoyant force acting on the body is equal to the weight of the fluid displaced, which is why boats can float, because they displace a large. This was a question in the ancient Greece. They had these big, large boats, and they couldn't explain. Well, they didn't believe they could float for, if they wanted to transport armies or equipment, right? They will, obviously, by then, they would think that they will sink. It was Archimedes who proved that that wouldn't happen because of this. All right? So wood, for example, right? A plank of wood can easily float. Why? Because of the Archimedes principle. There's a few problems I want to do, and you will see that in the next video, of course. The important thing that you have to take into account that the atmospheric pressure is greater near the surface of the Earth. That's because of pressure itself, the definition of pressure and density. The pressure near the bottom of the pool is, the more you are under the sea level of water, is always greater pressure. All right, you can think in terms of weight. You have the whole weight of water acting on you. So weight divided by your small area, more pressure. That's another way to think about it, by the way. Right? You go on the bottom of the pool, you start feeling the sensation in your ears because of the pressure. The weight of the fluid above contributes to the pressure, yeah, of course. Weight is mg. Now, density is mass over volume. So if density is mass over volume, mass is density times volume, which is this famous relationship here. Weight is equal to volume, density, yeah, we use rho for density, by the way, gravity. Volume is the area of the base times height, that's easy. And the pressure basically is force divided by area. So we have, here it is, right? So weight times, or the force of weight, is weight here, divided by the area, and then area cancels, and you get density, gravity times height. That's the relationship for, that's a equation for density, for pressure, sorry. So here's a nice experiment that we use sometimes in the lab, right? We place an object attached to a rope, and sometimes we place a balance. underneath the container, and you can see the difference in readings. That difference gives you the buoyant force acting on the mass. It's actually a very interesting experiment, right? So get this, the buoyant force is proportional to the bottom, to both the height and the cross-sectional area of the block, and thus to its volume. All right, so yeah, basically the buoyant force, guys, is the density of the liquid times the value of gravity times the volume of the body that is immersed on water. Now, a good question that people can ask, what if the body is partially in water? Which can happen, right? There are objects that float with part of its volume in water. We only take into account that part of volume that is in water. Again, you will see that in the examples. Now, fair enough, right? The questions in the exam are not going to be to ask, not going to ask you to do heavy calculations, maybe as simple like the ones you have seen in these slides. But still, I know some of you guys are very interested in this. The idea of fluids, liquids, it's actually very interesting, and to understand why objects float and the forces acting on them. For example, in this case, right, you have the tension on the rope, the weight, and then the buoyancy. So we can apply Newton's laws for that and solve for buoyancy or tension, right? What happens if the density of the object is greater than the one on the fluid? The weight of the object is greater, then it will sink. Metal, for example. If it's less than the fluid, it will float. If it's the same as the fluid, the object is equal to the weight, so the object can float, but it could be cases where it can also sink, right? This is a good example of how fish and submarines float. Submarines are made of metal, right? And that's because the object can float at whatever level by changing its density. So that's interesting, right? When the density of the object is the same as the fluid. Okay, so everything we have spoken about here is static fluids. But as you know, we have currents, we have rivers, we have fluids in motion, right? In pipes, for example. So we need to introduce a couple of new parameters. The first one would be the idea of viscosity, right? Which is basically the frictional effect within the fluid, right? Fluids are not frictionless, right? Not even air. We talk about air resistance, right? So there is viscosity, all right? And then we have to talk about the rate of flow or flow, which is basically the area of the cross-section of a pipe, for example, times the speed of the liquid, all right? This is very important for the continuity equation. This you guys probably have seen in the past, or you have experienced. When you are in an alley and when you are in a open environment, right? Like if you are in a street. You're in the street and it's a windy day, right? You will feel wind, but if you go into an alley where the area shrinks, you start feeling that the air hits you harder. Why? Because of the flow of air. At the end of the day, air is a fluid. You reduce the area, the speed of the fluid increases. All right, I always like to tell that to students. Sometimes they wonder why is that, right? That's the continuity equation. The flow of a fluid is always constant, okay? So if the flow is continuous, the rate of flow must be the same at any point. That's basically what I just said. The speed will also usually be greatest near the middle of the stream of the pipe. Yeah. The fluid can be made as a flowing of layers. Yeah. We normally apply that in physics. Because of frictional viscous forces, a thin layer that does not move is usually next to the walls. Yeah. So that's basically the fluid speed increases as the distance from the wall increases. Yeah. Okay, that's all due to the continuity and the way the liquid flows. Now, how do we, for example, so this is just a pipe horizontally, right? What about if you are trying to what if you're trying to increase the flow or increase the speed, the rate of a liquid from the bottom to larger altitudes, to higher altitudes. Right? This is a nice problem when you have a tank of water and you want to provide water to different floors. Right? It's all about pressure, density, and the flow of water. Now let's finish this, right? We have the laminar flow, which is a smooth flow, no eddies. Eddies, think in terms of eddies as currents in the water. The speed of different layers may vary, but one layer moves smoothly past another. Okay, kind of like frictionless. Turbulent flow does have eddies, so these currents, and the streamlines are not parallel. So normally we assume for problems laminar flow, all right? Turbulent flow is basically what you may have in rapids, in rivers, okay? You can still apply some of these, but you have to deal with other variables like eddies, and of course the idea of viscosity, right? For a fluid with low viscosity, the transition to the maximum speed occurs over a short distance there. If you have high viscosity, the transition takes over a larger distance, of course, because of friction, right? And we see the idea of high viscosity and turbulent flow, right? By seeing the increase of the fluid resistance through a pipe. But also in gas, right? For example, Jupiter and the red hot spot there, right? We know that this is a very huge storm, the size of more bigger than the size of the Earth. It's about 3-4 times the size of the Earth. The red spot of Jupiter, right, is stable, but it's an atmospheric eddy. And you actually see more here, by the way, right? That's because Jupiter has different layers. It's a Jovian planet made of mostly hydrogen and helium. There's not really a surface on it. So you have layers of clouds. Where the mantle should be, right? Where for us is rock, it has a mantle of liquid metallic hydrogen, right? So we can study the behavior of gases, right? And a lot of the idea behind what we understand from gases comes from astronomy, because by observing the gaseous planets, Jupiter and Saturn in particular, we have been able to corroborate a lot of our ideas of how gases behave. It's interesting, right? Okay, so the Bernoulli principle, guy, allows you to understand how the flow of a fluid works. Of course, we are assuming here the conservation of energy, so we're talking about laminar flow. So it's basically that the pressure plus 1/2 of the density times the speed squared is constant. So basically, pressure plus the kinetic energy per unit volume, right? Now, pressure depends on height. So we can apply this Bernoulli principle in tubes that are at different heights. Oh, there it is. Pressure plus kinetic energy plus the potential energy, density, gravity, height. So this is basically another equation for pressure if you think about it, right? And why do we need this? Because as I said, we can apply this principle to ideas of liquids flowing from one section of a pipe to a higher section of the same pipe. And again, when you look at the examples, you will actually understand this a bit more. But I would strongly recommend you guys to read the slides, of course, and then in the textbook, and watch these videos, by the way. Chapter 9, there are some exercises questions, but let me see if I can get here the textbook. Sometimes it doesn't work. Okay, so I think it's gonna work now. So let's see. Continue. Ah, maybe I can just access outside. McGraw Hill instructor login. Oh, I don't know the password for this. Can just access from outside. Mm-hmm. Wait, you have this book already with me. Okay, I have the book, but I wanna see the online. Oh, here it is, I think. Yeah, here it is. It's the first time I'm using Macro Hill, guys. I use Morse Engage. Okay, so if you go to chapter 9, here it is, right? So that was what we talk about. Here you have like values of density, so it's a bit more detailed. I would recommend 9.3 for sure, 9.2, 9.3, 9.4, and then 9.5. So the summary is also good, and make sure you watch this video, of course. And the second video I'm gonna upload after this, where I will go over the practice problems, and I will discuss with problems. I think sometimes it's better to understand some of these ideas. You have seen that in previous videos that I do. So I will go over this. Okay. And maybe a few more problems I have with me. So other than that, guys, I hope this lecture or this small video lecture help you to understand the slides a bit more, and then watch the next video to finish module 8, chapter 9 in the textbook. And then I will go into temperature and heat. I need to upload a few more videos here. This is actually a very interesting section as well. All right, guys. So I hope you guys have a nice rest of your day, and see you guys in the next video.